Surface reflection is a significant problem in applications such as liquid crystal displays, optical components, and solar cells because it reduces the contrast and the clarity of the image and the transmittance of the incident light. To prevent disturbances from external light and increase the transmittance of incident light, the main anti-reflective method is a multi-layer construction, yielding destructive interference in light reflected from interfaces between the different refractive index layers. Such a multi-layer structure requires both low refractive index materials and high refractive index materials to produce interference in the light reflected from the interfaces between the differently refracting layers. In the case of a single-layer coating composed of a low refractive index material, the reflectance is usually larger than 1.5% and limited to a narrow wavelength region. To produce broadband anti-reflection with less than 1% reflectance, the substrate must be coated with several layers having different refractive indices. The anti-reflective performance usually rises with an increased number of layers, leading to time-consuming, laborious, and expensive fabrications. The nanostructured surface also shows the anti-reflective properties. This characteristic is found in the cornea of night fly moths and other insects, and therefore called the moth's eye effect. Such surfaces can be made by lithography techniques, but the method is only suitable for small substrates and is expensive. In this invention, sub-wavelength nanostructured surfaces, simulating the structure of cornea of night fly moths, are fabricated by the deposition of monodispersed nanoparticles on the substrate to reduce the reflection of external light by virtue of destructive interference deriving from the grating theory. In contrast to multi-layer anti-reflection films, the invention doesn't need expensive low or high refractive index materials and a high-cost multi-layer structure of etching processes. Therefore, the invention has the merits of cheap raw materials and a simple process. In addition, the mechanic properties of the nanostructured surfaces are improved due to the design of a binding layer of polyethoxyloxane. In the invention, the transmittance is greater than 94% and the reflectance is lower than 0.8%, which meet most requirements of practical applications, and therefore has a greater potential in the application of optoelectronic products.